This is a conversation with Andrew Strominger. He is a theoretical physicist, the Gwil E. York Professor of Physics at Harvard University, and the director of Harvard Center for the Fundamental Laws of Nature. In this conversation, we discuss the mysteries of black holes, the no-hair theorem, black hole information paradox. We talk about soft hair, anti-de Sitter space, AdS CFT correspondence, and we also talk about quantum gravity and string theory. And let me just say, if all of these terms sound like gibberish to you, they also sounded like gibberish to me before I started working on this episode. And now they all make sense. And that's really been the premise of the show. If someone as dumb as me can understand these concepts, then I'm sure you can do way better than me. So I'm really excited for you to discover all of these exciting ideas. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, rate 5 stars in Apple Podcasts. This project takes a lot of my time, money, and efforts. If you'd like to see it continue, please consider making a donation on Patreon or Anchor. You can join as a member on YouTube, and members get early access to these videos. You can leave a gift on Instagram Reels, or you can also buy super thanks on YouTube. If not through monetary channels, then do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For other forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And mitron, now it's no time. In 1985, you were having lunch with Freeman Dyson at Princeton, and you were telling him about this superstring frenzy that everyone had fallen into. And he told you it takes people who are unreasonably believing and swept up in what they're doing. If you aren't like that, you won't be able to do great science. Let's start here. Does science and theoretical physics require an obsession or a mania? Does it require you to be completely committed to...
It does. Yeah. And that was such an interesting statement coming from Freeman Dyson, who was has his own views on quantum gravity, was mostly a critic. I mean, he was mostly a critic of string theory, which I was working on that time. And at that time in history, there was crazy, interesting explosion of interest in string theory. I mean, in the fall of '84, I was probably one of 2 or 3 dozen people in the world working on string theory. And 6 months later, Green and Schwartz wrote an important paper. I wrote an important paper with Candelas, Horowitz, and Witten, heterotic string, Gross, Harvey, Martinek, and Rome. 3 fantastic papers. And in 6 months, we went from a dozen people to probably 1,000 people working on it. Nothing like that has ever, that kind of sudden shift of interest of a large fraction of the community of theoretical physics. I haven't seen anything like that before or since in my career. And there was a lot of enthusiasm and a lot of unreasonable enthusiasm. Many of my colleagues, were sort of, you got the sense they were, booking their tickets to Stockholm, and, that physics was almost solved. And I've always prided myself in being a skeptic and, trying to see both sides of things, and everybody has their own style. And it's important that everybody has their own style. And I was not swept away. I was loving my work. I've always loved my work. I found it making the discoveries personally extremely gratifying and satisfying. And there's nothing more wonderful than, making new scientific discoveries and then having people interested in them. But I didn't buy a ticket to Stockholm. I didn't, and I was talking to Freeman, who I was good friends with them. I was just out of graduate school and a postdoc down at the Institute for Advanced Study. We had lunch together every Saturday. And I was telling him how I had not been swept up by the enthusiasm. And it's in writing there in some of my papers. Yeah. There isn't going to be a prediction of string theory that we're going to measure at an accelerator. And, but I loved it. And I felt like we were learning something, just wasn't clear exactly what. And I expected Freeman to pat me on the back. And, of course I looked up to him to pat me on the back and say, "You're so much smarter than all the rest of them." But he said exactly the opposite. And what he said was, it takes unreasonable amounts of enthusiasm. It takes people to believe in things that are very far away and to be very motivated by that to make great progress. And I there's a lot of truth in that, because if you don't, in the end, scientists are gamblers. They gamble on where they think progress will lie, where the truth about, for physicists, where the truth about the physical universe lies, and then you head in that general direction. And most people gamble and lose, We're explorers, So that's what it takes.
Scientists are like gamblers. I feel in gambling as well, there's a fallacy known as the sunk cost fallacy, where gamblers, they start betting towards a losing cause and then they keep betting in the wrong direction. Is this a problem in science as well? Newton gambled on the presence of the luminiferous ether. Kelvin had postulated in 1900s that we had reached the limits of physics. There's nothing new left to discover. And he said that in 1900, so 125 years ago. Many people say the same about string theorists as well, that in a way they've been swept up in the elegance of the models. There are critics of the Copenhagen interpretation and the Niels Bohr's models. Is it a challenge for scientists, academics as well, of not being able to tell whether the theory that you've gambled your life on, whether it's actually going to bear fruit? Because that's the only way. You have to be obsessed with an idea that's not bearing fruit, and then you'll push past the complexity of it. Or is it a challenge to not be able to tell that and not able to figure out whether you're fighting the wrong fight?
Yeah, it's a challenge. It's a huge challenge. Okay. It's like trying to find, like Lewis and Clark trying to get to the Pacific Ocean. They didn't know till they got there how many more mountain ranges there would be, which ones they could get over. Yeah. And of course, before Lewis and Clark, there were many people who got partway and couldn't get any further, and they came back with their partial information. This direction doesn't work. And so this, of course, I'm talking about fundamental science, okay? There's also various kinds of applied science which is equally important and satisfying, where you do know what you're supposed to do, and there's some fairly programmatic steps that you can follow, and you're almost guaranteed to get to some kind of result. That's right. If you want to test a drug, you want to test a drug. You get a population, you administer the drug, you do the test, and you get an answer. It works, it doesn't work. And either way, it's progress. What's different about the more fundamental the scientific endeavor is, the more likelihood there is that you'll go down some wrong alley, which won't be that fulfilling. But in the end, if you look at what happens in the history of our field, in the end, it seems that things always kind of come together, and somebody may try out a direction and run into an obstacle, turn around, and then 5, 10, 20 years later, we learn that it was the right thing to do. It was just one ingredient missing. And then you can go back down that path armed with the extra tool and make further progress. So I think many things fail in their immediate goal, but in the long-term goal, everything had to be done. All those different passes and so on had to be explored before we could really figure out the best way to get to California.
All those passes had to be explored to get to California. I'm going to take a digression and relate this to your own journey and your own life. You've said in a previous interview that you got into physics because it was so much fun, but you were great at many things. In high school, you were into drawing, poetry, politics. You were at the marches in Washington. When you were at Harvard, you dropped out to go live in a commune. You went and lived in China for a while. You got into Buddhist meditations as well. What was it about physics that you found fun and that attracted you? And then after seeing and doing so much in the world, after all these eclectic pursuits, what was it about physics that drew you right back in?
Well, I think physics contains the most basic kinds of truths that we can be certain of. So, we live in this bizarre universe. Weird trees out the window, buildings that somehow people learn to build, the sun goes around. It's so weird. Why is it like this and not some other? And the incredible thing is that we know so much about it. And I don't know how far we'll be able to get. Maybe there's no end to how much we can learn about the universe. Could we learn everything about the universe? The physical universe? Is there something else besides the physical universe? I don't know. But I think what's clear is that we can learn more definite things about the universe, and the way the universe is put together is just, I find it deeply beautiful. And it's somehow, I don't quite know how to describe it. It's just somehow really satisfying to, learn something. First of all, in high school, even in elementary school, it's wonderful to learn things about the universe that other people have discovered. How did they figure that out? Wow, that's amazing. The force of gravity that pulls the apple from the tree is the same. It's so cool. It's cool to learn about it. It's even cooler to figure, however small a piece. I've done nothing. I don't want to compare any of my own discoveries to understand that the force of gravity pulls an apple to Earth and makes the Earth goes around the sun. But even, infinitely smaller discoveries are still beautiful and awe-inspiring. And it's just really wonderful to do that. And I don't know what the universe adds up to, where it's all going, but it makes you feel engaged in it, makes you feel a part of it. So that's why I do it.
I definitely agree with you about the beauty in the universe and the magic of it. And I must say, your enthusiasm or your love for it, it reflects in all your work. I've watched a lot of your interviews. I've read a lot of your work. All of your work is dripping with this enthusiasm and excitement that you have for the universe. It's contagious. So in that spirit, I do want to explore.
But by the way, I might be a little better at expressing it, but they all feel it. You know, there's 40 people out there, professors, students, postdocs, and they all feel it, you know. It's the blood that flows through this. Yeah.
I agree. And bringing it back to Freeman Dyson, that's exactly what it takes to push past the difficulty of the subject, because it can get really complicated. So in that spirit, I want to start diving into your work and some of your discoveries. But before we go there, I want to define a few terms because we'll be referring to them multiple times. So I want to set the foundation so I can follow along. Let's start with the simplest definition first and get that out of the way. Black holes. What is a black hole?
So a black hole is the definition, mathematical definition of a black hole is a region of space-time from which light cannot escape. And the way that happens is that if the gravitational field gets too strong, then it can stop even light from pulling away. And so that's what a black hole is. They're black. Light doesn't come out of them.
We were talking about the magic of the universe. Black holes are objects that I find close to magic or magical. They're such mysterious objects. Let's get two more definitions out of the way. What is the event horizon and what is a singularity?
Okay. So the event horizon is it's just the outer boundary of the black hole. Okay. It's the boundary of that region. The black hole is the region of space-time itself, and the event horizon is the edge of it. Okay. And since light can't get out from the region, we can't see beyond the event horizon. We can't see into a black hole. No light comes out of it. Singularity is a much more complicated concept. So a singularity, so I told you what a black hole was. Indeed, people, without ever mentioning Einstein or the Einstein equation or curved space-time. And in fact, the existence of objects from which light could not escape, a black hole, was hypothesized by Michel, I think his name was, a century before Einstein. So it's a more kind of basic concept. Now, Einstein wrote down his equations, which govern the gravitational field and the structure of space and time, and showed that Schwarzschild showed that they contain solutions that are black holes, that have regions of space-time from which light cannot escape. Using those same equations, it's also shown that inside that is a so-called singularity. And a singularity is a region of space-time in which, so space is curved in Einstein's theory of relativity. It's not flat like this tabletop. It's more rounded like the surface of the microphone. And that it gets more and more curved as you go deeper into the black hole, and in the middle of it, actually the curvature becomes infinite. And that's a signal that Einstein was alarmed by it, but it's not really so alarming. It's just a signal that the Einstein equations are out of their league in the middle of the black hole, that you need more than the Einstein equation. And of course, we've long known that the Einstein equation it would be very, very strange if the Einstein equation were the last word on the structure of space and time. We expect more. Everything that we learn gets corrected in certain situations. Everything that we know about the physical universe is approximate. For example, Newton's theory of gravity is pretty good. It predicted everything we could see for centuries. Then we got some really precise measurements, and turned out that it gave the wrong answers which were wrong by 1 part in 100 million. Really, almost right. Just 1 part in 100 million for Mercury's orbit around the sun. Okay, so and then General Einstein's theory gets that right. So it's almost like Newton's theory, but it's a little bit different. Someday, for sure, in this, there are a few things I would say with such confidence, but someday, for sure, there will be some theory which is better than Einstein's general relativity, more accurate, works better, is some kind of correction of Einstein's theory. And we know that has to be true because Einstein's theory is ultimately on its own not compatible with quantum mechanics. Okay, there could be some error in our reasoning, but no, it seems highly unlikely. So there'll be some better theory that corrects Einstein's and can deal with the singularity in the middle of the black hole.
So as things stand with Einstein's theory of general relativity, there's no way of predicting what happens if I enter a black hole. What's going to happen to me? Nobody knows.
That's right. Okay. That's right. Yeah.
Okay. Well, black holes, like I said, magical, mysterious objects. I want to continue exploring some more mysteries of the black holes, some of which you've tried to solve. First, let's tackle the problem of their hairstyles or their lack of hairstyles. Leo Tolstoy's Anna Karenina, it begins with this really popular line, all happy families are alike. Each unhappy family is unhappy in its own way. John Wheeler used to believe that black holes are like happy families. They're all exactly the same. He and Jacob Bekenstein came up with the phrase, black holes have no hair. And you've called John Wheeler one of the greatest phrase masters in physics. This is definitely a phrase that stuck because it became the premise for the no hair.
He also invented the word black hole.
Multiple phrases.
Black holes have no hair.
John Wheeler can take credit to multiple phrases in physics. And this became the premise for the no hair theorem. So let's define all of these terms. What is the no hair theorem? What is hair in this context when it comes to black holes? And then what does it mean when he says, along with Jacob Bekenstein, that black holes have no hair?
Yeah, so if you look at 2 stars in the sky, you could have 2 stars which had exactly the same mass, exactly the same total luminosity. But if you looked at them with more and more detail, every star, there are millions and billions of stars up there, every one is different in innumerable ways. Every star has, trillions and trillions and trillions of atoms in it. And they might be different elements, and they'd be moving in different ways and different temperatures, and there'd be magnetic fields and all kinds of detail, right? Every star is different. But the weird thing about black holes is according to the theory of general relativity, there are only two things that characterize an astrophysical black hole. That is its total mass, and they also spin. Right. One of the really interesting things about them, their mass and their spin. And if you have two black holes with the same mass and spin, they're exactly the same according to general relativity. And so you could have two stars which were very different with the same mass and spin. And stars can sometimes collapse under gravitational pressure under certain circumstances and become a black hole. So you could have two stars which were very different, and then they would collapse into a black hole, and what would be left of the black hole would be not just approximately the same, but exactly the same. And that, at least as far as we know how to describe this situation with general relativity, it tells us that they will be exactly the same. And I'm sure you'll ask me about that later. It's related to the information problem, but it's very troubling that two things which are different can become the same. And that's what John Wheeler meant by saying black holes have no hair. There aren't distinguishing features classically on a black hole.
They're bald.
They're bald.
Right.
Yeah.
Let's talk about the information paradox as well. This is another mystery associated with black holes. What is the black hole information paradox?
Yeah, so I just got very close to describing it. But in its sharpest form, we would first have to have a conversation about quantum mechanics and black holes. But maybe this is the most primeval form. If we have two stars, they have a lot of information in them. One of them could have a giant computer orbiting around it or something, and it could all collapse. There could be information would be lost because we wouldn't be able to reconstruct from the final black hole, which has no hair, what the initial configuration was. And so that's a piece of the information paradox.
Right. So that violates the laws of quantum physics because information should not be lost. Worst case scenario, it can be scrambled, but should be conserved.
Right.
You published a paper in 2016 along with Malcolm Perry and Stephen Hawking, where you refuted John Wheeler and Bekenstein's claim that black holes are bald in nature. You've implied that they are not like Tolstoy's happy families, but they're like the unhappy families. They're all different.
Right.
And you've said in that paper that we found that black holes are not entirely bald. They can carry soft hair, low energy quantum excitations that might encode information about what fell in. So this seems to address both the black hole information paradox and the no hair theorem that we just spoke about. So let's dive into it. What is soft hair? And then how does it address these two mysteries or paradoxes we just talked about?
Okay, so first of all, soft hair. So it's not quite exactly true that it's not quite exactly true that so it's a modification of Wheeler's observation already at the classical level. So one thing one might have said was, well, wait, what about a black hole that's moving? Is that the same thing as a black hole that's still? And so there's a subtle difference there. And And how would you, so of course everybody would want to say that a black hole that's moving is different than a black hole that's not moving.
Even if they have the same size and spin.
Yeah, even if they have the same size and spin.
Right.
Right.
Okay.
However, they're given by, you have to add a little more structure to distinguish them. You have to have sort of an observer, which you would usually put out at infinity. And so I'm putting something in which I'm trying to put something on which there is sort of half a century of very precise and detailed mathematical work into simple words, okay?
No pressure.
Yeah. So the way that you would tell the difference between a moving black hole and a stationary black hole is you would have to have some structure at infinity, moving relative to something, right? Moving relative to some observers out at infinity. That's how you would say it, okay? We have a fixed reference frame. Now, it turns out that it's very hard to specify exactly how this reference frame works in Einstein's general theory of relativity because general relativity is a theory in which space-time itself, other theories like Maxwell's theory of electromagnetism, you fix the space-time. It's like fixing the blackboard. And then you write the equations and everything moves around, but you've got some reference that you can pin everything against.
Everything's emergent from that fundamental.
Yeah, everything's emergent from that fundamental thing. In general relativity, you don't have that luxury because it's a theory of the blackboard itself. And so you have to ask, what is that relative to? What does it mean the black hole is some curvature present on the blackboard? What is it moving relative to? Okay? So this turns out to be an incredibly subtle problem. And was first realized by Bondi, Metzner, and Sachs in the 60s, and in different ways in a very different way by Steve Weinberg in a completely different mathematical language. That the ambiguity in describing something, any object, not just a black hole, it's not just whether something is stationary or moving. There's a lot more kinds of ambiguities. So one way of saying it is you have to ask how exactly the black hole is situated relative to infinity. And it's not just whether it's moving or not. There are infinitely many different parameters involved in a black hole attached to observers at infinity. It's the relativity principle. Yeah. Everything is relative. What is the black hole relative to? Relative to infinity. And that actually gives us a number of very well-defined hair that we can associate to a black hole. There are experimental predictions related to this hair, the so-called memory effect, that they're probably going to be measured in the next decade or so at LIGO or at LISA, and there's a very beautiful mathematical story there. Now, this is going to explain the relevance to black hole information, but let me just, do you have any questions about what I said so far?
Many questions, but let's complete the story. I'll just drop a comment that while you were talking about fixing a reference point that's beyond the system, it reminds me of Gödel and Gödel's incompleteness theorem that you can't make predictions about a system while you're in it. So you have to have an external reference point or an observer to actually make predictions about something within the system. Am I making the right analogy?
It's not unrelated.
Okay.
It's not unrelated.
Close.
It's a theme. It's a theme in physics that there are often surprises when you dig down and try to be precise about exactly what you could observe or measure. It's not as simple as you thought. And of course, it's famously quantum mechanics. We can't measure what we thought we could. And here it's the opposite. There are more things that we can measure than we thought. And so that shows that Wheeler was subtly wrong. And it is true, the theorems are mathematical theorems that there is no hair, but they're not relevant to real-world black holes in which we always relate them to some observers at infinity. And then all of a sudden the situation is rather dramatically different. Now that's the so-called soft hair on black holes. Now, this is a flaw in Hawking's argument that black holes destroy information. Whether it's the flaw and there's some totally coherent picture when this is all taken into account, or whether it's just a technical complication, the jury is still out.
So these software help you in distinguishing black holes, but are these actually physical objects?
What?
The software.
Yeah, they're measurable. They're measurable.
So what are they?
Well, they are distinct solutions to the Einstein equations, right, with different kinds of soft hair, right, and you can measure the transition between one kind black hole with one kind of soft hair and black hole with another kind of soft hair.
Right. So these are attributes or properties of the black hole, but not exactly like particles.
Well, they're attributes of a black hole tied to infinity.
Gotcha. It's the perfect time to introduce the holographic principle. So what is the holographic principle?
Well, the holographic principle, there was before the holographic principle, I have to tell you something about black hole entropy or black hole information storage.
The Bekenstein-Hawking entropy?
The Bekenstein-Hawking entropy, yeah.
Okay.
So Bekenstein and Hawking, and actually Wheeler was Bekenstein's thesis advisor, I think, yeah, and also involved in this, argued rather convincingly that black holes are capable, they can store a certain amount of information, and there's a formula for that, which is really that formula is one of the, well, I teach a freshman course in the laws of nature, and I try to teach them. This is for non-physicists, and I teach them about three equations, which I regard as the most important, most interesting to me equations from 20th century physics. And they are the Einstein equation, the Einstein equation of general relativity, the Schrodinger equation of quantum mechanics, and the Bekenstein-Hawking entropy formula. And that one, it's a very deep equation. We don't really fully understand it. We really don't fully understand it. And what it says is that the amount of information you can stuff into a black hole is proportional to the area of the event horizon. And that's a very strange thing because, if we wanted to, store information, put computer chips into this coffee cup, the amount of information we could store would be proportional to
the
volume of this coffee cup.
Yeah.
Not the surface area. Right. Somehow, if you could only tile them onto the surface, then the amount of information would be proportional to the area. So that is very strange. And it suggests, in this case, that the region of space inside the black hole is described by some more ordinary system. Clearly, the black hole isn't an ordinary object, but it might be describable by an ordinary object that just lived on the surface. And that is the so-called holographic plate, right? That would be the holographic plate. The black hole itself would be the emergent hologram. So it suggests the hypothesis that any region of space-time, or physicists have slowly been getting interested in, and the idea that any region of space-time can be described, not just the interior of a black hole, described by some quantum system that lives on its boundary. Now, this sounds, forget about whether it describes the real universe or not that we live in, it sounds wacko. However, using various tricks in string theory, we've been able to show that we've been able to find some situations where exactly this happens. So the first example was in string theory was where Vafa and I showed that certain kinds of black holes were described by some other object that lived on the surface of that black hole, a conformal field theory. And that was then generalized by Moldacina to whole universes, so-called anti-de Sitter universes. They don't look like our own universe, but they are solutions of the Einstein equations, and so on. This is all within string theory. They can be described holographically by something that lives on the boundary.
Just to clarify, what is an anti-de Sitter space? This is something I always struggle to visualize. So if you can explain to me, like I'm a 12-year-old, which is my mental age anyway, what is an anti-de Sitter space?
Well, there are three sort of simplest spacetimes that solve the Einstein equation. The very simplest one is just empty flat space. That's a solution of the Einstein equation. But now you could add to the Einstein equation another term, which Einstein himself considered
his blunder.
In the 30s. Yeah. And we actually astronomers now believe that there is an extra term which is weirdly very, very small. It's often called dark energy, but it's an extra term in the Einstein equation. And if you add that extra term, flat space is no longer a solution. But there is a very simple solution that replaces flat space, and it's a space where a moment of time is a big sphere. That's for a positive amount of, that's if the dark energy is positive, okay? A round sphere. Something that's called de Sitter space. Okay. That was discovered a long time ago. And also anti-de Sitter space, also discovered a long time ago, is what you get if the cosmological constant has the other sign. And instead of being positively curved like de Sitter space or like a sphere, it's negatively curved like the surface of a saddle.
Okay, like a bowl.
No, bowl would be positive curved. It has to be,
I hear you. A saddle is the right description, I guess.
Okay, a saddle
Yeah.
is the right. You don't have any negative.
No saddle-shaped Lego. I'll drop a complaint to the makers of Lego.
Yeah.
Need to have some anti-de Sitter inspired.
Yeah, they are harder to visualize. And interestingly, the saddle thing, the sphere closes in on itself. Flat space goes off to infinity. And the negatively curved space also go out to infinity. And in that case, in some stringing examples, you can show with kind of mind-boggling mathematical detail that everything that happens in the whole anti-de Sitter universe is encoded. We can think of the whole universe as a hologram, which is projected from the holographic plate, which lives on its boundary. So there's no question that, this convincingly demonstrates that it's not a mathematical contradiction to say that a region of space-time can be described by something wholly described in complete detail by something which lives on its boundary.
This is the AdS CFT correspondence. Right?
This is the AdS CFT correspondence, yes. And now, that is not the real world for several reasons. First of all, we don't live in anti-de Sitter space. And second of all, string theory might or might not be the real world. So, so we've got plenty of work to do. We'd like to understand the holographic principle without invoking string theory.
Mm-hmm.
And we'd like to adapt it to universes like our own.
Let's bring philosophy into the picture. Taking philosophical digressions is one of my biggest weaknesses. John Wheeler had published a paper titled Information Physics Quantum, The Search for Links, in which he had said, every physical quantity, every it, derives its ultimate significance from bits, binary yes or no indications, a conclusion which we epitomize in the phrase it from bit. The holographic principle implies that this universe that I perceive, this 3D reality, is a projection or a hologram of this information on a smaller space or lower dimensional space. And as a result, it requires me to shift my perception of the universe from this fundamental materialistic universe to this information layer that's even beneath it. It puts this information layer as the fundamental layer, the grounding layer from which everything else emerges. Would that be a fair assessment? If I become an advocate for the holographic principle, does that require a shift from this materialistic viewpoint to maybe information realism or some variation of Platonism?
Well, I think in this, let me clarify what I said a moment ago. So there's two things which are equivalent. And we often, we could say, so my cup of coffee, we could say, we could say that this cup of coffee is 95% empty, or we could say it's 5% full. Okay, those are equivalent statements. You can't say which one is the more fundamental than the other. Okay, they're just too true and they're equivalent. Now, in the holographic realization of quantum gravity or whatever, and holographic instantiations of quantum gravity, you can't say that the hologram is more fundamental than the holographic plate. They're just equivalent. If you know the hologram, the image, you could reconstruct what the plate was. And if you know the plate, you could reconstruct what the image is.
But clearly one is emergent from the other, right? In metaphysics, this is called grounding of fundamentality, right? One is causing the other.
Yeah. That is a problem with the hologram analogy. Okay? The hologram analogy suggests that, but in reality, in the mathematical description, it's just like the 95% and the 5%. It's an equivalence. Now, it's the mathematics is, here, which is 100% minus 5% is 95%. That's all the mathematics. To understand the equivalence in the AdS CFT correspondence, that involved, understanding whole new realms of mathematics. In some cases, new mathematics had to be developed. It's very non-trivial and not very obvious, and at first even seemingly impossible. Yet at the end, it works in some examples. And now, when you have two representations of the same thing, even though they're both equivalent, it might be that some questions are easier to answer in one than in the other. Like if I say that there's only 5% of the coffee left, if I want to know how many more swigs I can take, it's a little easier from the 5% than from the 95%. What you're going to do with the 95% is you're going to subtract it from 100%. Oh, 5%, you've got 2 swigs left. Yeah. The same thing, like if you have when I was a kid, actually, I had a hologram, which I got from Edmund Scientific Company. And, there was a little plate, and you shine some kind of laser from it, a little chess piece. You'd have had a very hard time looking at the plate to understand that the image was going to be a chess piece. That information would be very obscure from the plate. On the other hand, from the image, you'd have a hard time knowing how many pixels of information are required to put it together. On the plate, you could just sort of count them up, So the two descriptions have different utility, but ultimately they're equivalent. Ultimately, if you worked hard enough, you could analyze the plate and reconstruct the trajectories of the light rays and understand that the chess piece was going to pop out. Conversely, you could analyze the image and know how much,
So it's like a shift in perspective.
Shift in perspective, yeah.
Okay. While we're dabbling in philosophy, let's also talk about
Well, I was not dabbling in philosophy. You were trying to get me to dabble in philosophy.
While I'm dabbling in philosophy.
And I would not go over the line.
Let's see if you go over the line with this question. I want to talk about determinism.
Yeah.
As long as the black hole information paradox was valid, it felt like determinism was out of the picture because information was getting lost somewhere. And this may sound crazy to you, but it felt right to me. It feels right and intuitive if the universe is not deterministic, if there's no Laplace's demon. With the findings in software and with the findings that information is being encoded, it's not being lost, it's being conserved. It feels like determinism is making its way back into the picture. It's not fully there yet, but it's starting to wedge its way back again. It feels like Laplace's demon is getting some temporary life again. Would you agree with this assessment? And then do you have a hunch whether the universe is fundamentally indeterministic or whether it's fundamentally deterministic?
Yeah. So I think the universe is probably not deterministic, though you probably would have to work harder to define exactly what determinism means. And the reason I think that is the Big Bang, right? Because we think that before the Big Bang, there was nothing. And then afterwards, there was something. And there isn't really a deterministic map from nothing to something. So at least determinism in the way we usually think about it as being able to evolve in time forever. If time stopped, the laws of physics enable us to go into the infinite future and the infinite past. That doesn't seem possible if you have a Big Bang. On the other hand, so I think that ultimately determinism will go the same way as the other things we thought were obviously true, like the Earth is flat, and then the Earth is the center of the universe, and time is absolute, and all those things that we thought were true. The history of physics is the history of discovering that things we were absolutely sure must be true are actually false. And I think determinism will ultimately fall into that basket. But I don't think that that's going to happen now. In other words, I don't think we're progressed to a point where we can understand how we can describe the universe without deterministic laws. One might have thought, and many people did think, that black holes themselves were the end of determinism. Hawking certainly thought that. Mm-hmm. And even the classical relativists thought that in a way, depending on how you parse their statements. But I don't think that's how it's going to go with black holes. And most people would agree with me. And the reason for that is it's not a scientific proof, but it's just kind of Occam's razor. And it's where I'm gambling. And my view is it's true that we don't know if string theory describes the real world, but we know that string theory have black holes, and we know that we can we can count the number of states of a black hole in some string theory settings. And it agrees with exactly what Bekenstein and Hawking predicted. And just to connect your earlier questions with this one, determinism is the same thing as preservation of information. If information is destroyed, there isn't determinism. And so why would a black hole be capable, if we found that black holes destroyed information and therefore violated determinism, why would they bother to have exactly the right number of internal configurations, the right number of gigabytes to store all that information? It would be sort of useless. So the prettiest picture, which I always vote for, because it always ends up being, if you think you have your prettiest picture, and then the universe always takes the most elegant solution to, in the history, it's always the most beautiful solution. It's nobody's ever come up with a beautiful theory that seems to describe things well, and then it's wrong. And okay, it doesn't mean it won't happen someday, but but we're gamblers, and so the simplest thing is that there is some way that the information is preserved. That's not a proof that it is, but that's why I'm trying to understand exactly how it is that information is not destroyed by black holes, rather than trying to prove that it is destroyed by black holes, or trying to find a consistent generalization of quantum mechanics in which information is destroyed by black holes. People worked on that. They didn't get anywhere. Could be most people are wrong, and someday somebody will come up with a theory which is not deterministic and explains the behavior of quantum black holes. It could happen. It's still on the table.
As things stand then, if I was building an AI model and I'm trying to find all these laws that explain the universe, would it be fair to then optimize for elegance and beauty? Because it seems to be such a successful model that if I'm only optimizing for elegance, it's quite likely that would actually be the law that explains the universe.
Can an AI? I don't think AI can do that now.
This is like this is a Gedanken experiment.
Experiment.
If I'm optimizing for, or even if I as a human being, I'm trying to find the laws of the universe, should I be optimizing for elegance and beauty? Because that seems to be leading us in the right direction.
I would never use the word should. You could try, yeah. I mean, that's what I do, yeah.
Okay, well, I'm going to try. I'll keep you posted. Let's come back from these philosophical digressions that I was trying to dabble in, and let's come to more concrete implications of these findings. You brought up quantum gravity earlier. Many years ago, when you were at MIT, your thesis advisor advised you to not work in quantum gravity because he said you'll probably not find a job. And then decades later, when he introduced you to a colloquium at MIT, he said, good thing he didn't listen to me. So let's talk about quantum gravity. What is quantum gravity, and why was it such a risk to your career back then?
Yeah, so, quantum mechanics and general relativity are the great pillars of fundamental physics of the 20th century. And, both of them have been tested to many, many decimal places. And they're definitely true in some domain. And, general relativity is really good for computing, orbits of, planets around the sun, and we see black holes in the sky now, and we can look at, accretion disks around black holes. All of that is perfectly described by black holes. So general relativity is mostly important on large scales, and quantum mechanics is not very important on large scales. On the other hand, small things, structure of atoms. Atoms would be unstable if without quantum effects. And they are, for small things, quantum mechanics is crucial. Now, but in principle, in a complete theory, even if we can't measure it, often we can compute properties of things before we can measure them. And from our theory, we should be able to, in principle, compute gravitational corrections to the energy levels of the hydrogen atom, or quantum corrections to Mercury's orbit around the sun. Fabulously small, 40 orders of magnitude, depending on what 40 orders of magnitude smaller than anything we've ever been able to measure. Not going to happen soon. Nevertheless, the fact that they both coexist peacefully in the world around us means that there must be some consistent way, there must be a theory which reduces to general relativity on long scales and quantum mechanics on short scales and describes everything exactly at all intermediate scales.
The theory of everything.
Well, I don't necessarily mean, theory of everything, but that's yet another axis of things that we don't understand. What are all the particles in nature? So all the other particles, the electron, the muon, the photon, they can all be described, their interactions can all be described in a way which is perfectly consistent with quantum mechanics. But gravity doesn't allow the yoke of quantum mechanics around it. And again, it has to do ultimately with this thing that we were describing before, is we write quantum mechanics on the blackboard, and then the blackboard, we have the uncertainty principle, and the blackboard becomes uncertain, and we're at a loss. We're at a loss what to do, and we need to find the right mathematical framework. And so that is the problem of quantum gravity. So it's not so much about including all the other particles and finding out what all the other particles there are, though string theory addresses both questions, right? String theory gives you complete theories with complete spectrum of particles and reconciles quantum mechanics and general relativity, but they're logically different questions. You might come to a much greater degree of understanding of quantum gravity than what we have now. What kind of structures do allow quantum mechanics and general relativity to fit together, without answering the question of what are all the particles in nature, including the ones that are too heavy to have been seen at the Large Hadron Collider. We don't think that we've seen, we saw the Higgs boson, whatever it was, a decade ago. Yeah. That's the heaviest particle, fundamental particle we've ever seen. Few people think that's the last one. There's more than that we don't know about, and maybe we'll never be able to see them because we won't be able to build a big enough accelerator. Maybe we'll build a bigger accelerator and we'll find some more, but then there'll be still more. So those are logically separate questions, both of them incredibly interesting. But the problem of quantum gravity, and it may be that you can't solve them separately. It may be that you have to solve them at the same time. And that's what string theory did. Solved them at the same time, and except found a mathematical solution. We don't know if we can't do the experiment to test if that mathematical solution is the one that nature adopts. But I think there's a lot more to understand about quantum gravity that doesn't assume string theory. When I was a graduate student, our field, like many fields, it gets concentrated on one subject, and and there's definitely some element of faddishness among everybody. Everybody in the world gets tracked into some set of beliefs and what you should work on and so on. Physics was, at the time I was a student, the important problem on which you were supposed to work was either finding the so-called grand unified theory, which unified the quarks and the leptons, or understanding how quarks are confined into protons. So the strong interactions are unifying the strong with the weak. Nobody was interested in gravity. Very few people were interested in gravity, like as in dozens in the world. Quantum gravity, dozens of people in the world. And, I thought it was a beautiful problem, a well-posed problem. I'm a little bit of a, what's the word? A little bit of a contrarian. I don't like to work the same thing as everybody else is working on. And that serves me well as long as the other thing I'm working on is something good. And it turned out I was in luck. And I looked at the problem of quantum gravity, and it's such a well-posed problem, and it involved a mathematical conflict between two fundamental parts of physics, and in the history of physics, we've learned a lot. When you have a conflict, when you have a contradiction, that's something you can dig into and try to resolve. And so that's how I got interested in quantum gravity. But at that time, it was definitely frowned upon to be working on it. So I wrote a couple of papers on it in my thesis, but they didn't count for my thesis. My thesis was but it was the thing that I developed later. Yeah.
Just a hobby project on the side. Quantum gravity doesn't count towards your thesis. Does the AdS CFT correspondence contribute towards quantum gravity? Does it actually push us in that direction?
Absolutely. So AdS CFT is something that was derived by thinking about string theory and black holes in string theory, but it's an example of something that we can understand in string theory, and it's the most sort of complete and intricate realization of the holographic principle. And the way I would put it is this: string theory is endlessly fascinating, and it puts things together that seem like they don't want to go together. Right. So string theory, performs the seemingly magic trick of reconciling quantum mechanics with general relativity, and at the same time reproducing the Bekenstein-Hawking entropy formula. Now, without assuming string theory, you can take lessons from string theory. How did these irreconcilable phenomena seemingly irreconcilable, become reconciled? There's a mathematical route by which one can be transformed to the other. So you can take lessons from string theory and try to apply them to the real world without assuming string theory and see if you can start, you know what to shoot for. See if you can start from what we know about the real world and show that things seemingly disparate observations about the structure of the real world can be reconciled using the same kind of mathematical structures that string theory does.
It's become cool to hate on string theory lately. I've interviewed quite a few professors, academics on this show who've had harsh words to say about string theory. I've had Tim Maudlin from NYU on the show. I've had Pascal Wallisch, who said string theory has become like a religion. I've interviewed Peter Voigt, who is famous for saying string theory is not even wrong because it's not even falsifiable. So it can't even prove whether it's right or wrong. It's not even wrong. Eric Weinstein is popular for saying string theory has brought physics to a standstill. String theories are lost in the elegance of the models. You've said in the past that string theory is nothing but a tool. And the problem starts when people
I didn't say nothing but.
You said string theory is a tool, and the problem really starts when people start thinking it's the universal answer to everything, or it's the answer, it's the ultimate answer. Where do you think string theory is now? Is it still useful as a tool? Can you still extract more juice from it, or do you feel string theory is now hit a dead end, and it's better to move on to other theories?
String theory, well, first of all, string theory is a tool. Nothing but a tool. It's the best tool we have. Okay. So many problems in physics have been solved by mapping it into some problem in string theory, and then even in condensed matter physics, and by mapping it to a problem on string theory, see how string theory solve it, and then mapping it back. Been the most prominent in pure mathematics, right? So take a math problem, map it to string theory, then you use string theory tools, you find out what the answer is, and then you go back, and there are phenomena in pure mathematics, and now, they can see how it works by looking at how it works in string theory, and then you can throw out the string theory and prove it from start without ever saying the word string theory, okay? So, any theoretical physicist who doesn't know string theory, hasn't studied string theory, is crippled. They don't have all the tools that other people that other people do. So I think the whole thing is a little bit, I would say, kind of silly. I present when I give public lectures on string theory, I have a report card, a string theory report card. Right. And there are various things like, what would you think of what might you hope string theory could accomplish? One is provide an experimentally verifiable prediction. Produce experimentally F. Okay? Give an example of a theory in which black hole entropy that contains quantum mechanics and general relativity, B+, And so I have this whole report card. Nobody really disagrees. Even Peter Voigt, I don't think, would disagree with the different grades that I have given. Now, So it is what it is. It's not nothing and it's not everything. And if we want to go into uncharted territory, we should know what tools are there for us to use. It's like, like Lewis and Clark trying to get to the Pacific Ocean and saying, I'm not going to bring, a muskrat trap because I don't know if there's any muskrats between here and Pacific Ocean. You get halfway and you're in muskrat territory and you have nothing to eat. And, you got a muskrat trap. You're in good business. You're in good shape. Yeah. So, it is what it is. Now, another thing that there's a lot of sociology in all of this, of course, right? So there was a time, and this goes back to that beginning of our interview, we were talking about all the excitement about string theory. The people who thought they were ready to get their plane tickets to Stockholm went around saying some pretty extreme things which might have come off as a little arrogant and rubbed people the wrong way. Yeah. And so Peter Voigt was probably one of the people who was rubbed the wrong way. It's very interesting though. As you can tell, I love string theory. I think we've learned a lot from it. I don't think we know that it's the theory of the world. We've learned a lot about, for example, possible behaviors of black holes, mathematically self-consistent behaviors of black holes. And where everything will land, we don't know. But I think it's all incredibly interesting and exciting. And I recently was on a panel discussion on the status of string theory, Brian Greene and the World Science Festival. And I was expressed enthusiasm. I'm enthusiastic. Expressed enthusiasm about it. I think it's a great adventure and it's a privilege to be part of it and really fun. And Peter Voigt at the bottom of the show wrote, but at the same time, I made the statement, we're not going to have any measurement for string theory. Yeah. And Peter Voigt wrote in the comments, Strominger has brought string theory hype to a new level. Now, by the way, he likes the other stuff that I do. And he said good things about it, which are pretty rare for him to say good about anything. But he said some good things about it. Now, what's interesting about that, and I thought about what he wrote a long time, because I felt I was expressing my own personal joy at how interesting it was, how much I enjoyed it. Not telling anybody else they should work on it, not, But when I read his comment, it wasn't too hard to imagine. It's a fine line. And it's one of the hard things about doing interviews like this. I mean, at the end of the day, I'm just going to answer the questions and say what I think and be myself. But loving what you do, being enthusiastic, I don't think I'm telling anybody else to work on what I'm working on or, but many people want to. Many people also find it exciting. So yeah.
I think it's a reflection of the progress physics has made, that so many people are so committed or so intensely passionate about where physics is heading and where brilliant minds like you are devoting all their energy. So I think it stems from love for the subject and wanting you to do different things, which is better than indifference, I think, in physics.
By the way, I stopped you from using the word should.
Right.
Because I'm no, if somebody wants to work on, some other approach, I'm not going to say they shouldn't do it, and if they want to work on move from string theory to condensed matter theory, or I'm not going to say they shouldn't do that. That's not interesting. The really interesting stuff is this, or everybody should do what they are interested in. There's no one right thing. And if anything, I think that what our field suffers from the most is, a kind of herd effect where people, it's better if people are doing their own thing and exploring different directions. And that's the way to explore all the intellectual territory out there.
I definitely agree with you. On this show itself, I've spoken to many people that some people might consider have radical ideas, but we've covered the transactional interpretation, we covered the many-worlds theory, Wolfram physics as well, and Twistor theory. And I just feel even if they hit a dead end, just the pursuit of these ideas, it's a great way to just unlock ways of thinking, because they have, in a way, opened gates for me of visualizing the world in a slightly different way that I've never done otherwise. So just for that reason itself, I think these pursuits are quite valuable.
Twistor theory is a great example because, I started out with some mathematical observations by Penrose in the 60s and 70s. And it tried to be a quantum theory. It tried to solve the problem of quantum gravity. Right. And along the way, there was some really deep insights about the structure of space and time. And in fact, this structure of the relationship of infinity to the black holes and all that stuff is buried in there. And I didn't understand why so many people worked on Twistor theory, and I didn't think it was going anywhere. And then all of a sudden, in the last 5-10 years, went into string theory, came out, tried to apply it to flat space, and then we found some beautiful connections to Twistor theory. Now I'm, postdocs who work on Twistor theory, and I've learned it. There's all kinds of beautiful connections, and its relation to other things has, so that's the norm. That's the norm.
There's definitely a lot of value in pursuing these ideas and just adding these tools into your toolkit. Let's start wrapping up. Before we move into the closing questions, I would love it if you can tell me what masterpieces I've built with the Lego. What do you think these objects are?
This looks like a stairs up to a diving board, but you need a little diving board here. Here we go. There we go.
It was incomplete.
Okay,
You've completed it. I'll give you equal credits for that final edition.
Now you've got a diving board. Okay. This is a window with a little fireplace with it. You could have a fire in there, a two-way outdoor fire pit. Fire in there, and then this would be the smokestack.
Perfect. Exactly what I was building. And with your important addition, now the picture is complete. Let's move into some closing questions. What are some books, movies, role models that have strongly inspired you in your life?
Books, movies, role models. Well, yeah. Of course, Einstein. But it's interesting. People are complex, including Einstein. Yeah, people are complex, including Einstein. He wasn't very, when I learned more about him later, he wasn't very good to Poincaré, who had a lot of special relativity. Never referred to Poincaré. And when I read Poincaré's papers, it was really special relativity. In my opinion, it was special relativity. He had all the equations of special relativity, but didn't say it as beautifully as Einstein did. And we know that Einstein studied those papers. Okay, but he did great things, but he was also, a complicated human being and kind of arrogant in his setback. I think, confused everybody about what quantum mechanics was, because he didn't fit into his worldview. Yeah. And then there was his disturbing letters that he wrote to his wife and his son that just, okay, so the myth of Einstein, of course, was a role model. But all people are complicated. I'm complicated, and good things and bad things. But as someone who inspired me, certainly Einstein. My parents are wonderful people. I got a dad who's 100, about to be 100, still alive. He's very inspirational. Also complicated figure. Yeah. I had a great, if we're talking about physics, I had a lot of great friends too. I've had a lot of great friends. Yeah, I'm lucky to have a lot of great friends that I talk to about all kinds of things. Hard question to answer. Probably the I was very interested, in my early teens, or even before that, in Buddhism and those, I read many of those things, and I don't know if I have a good answer for it.
A book recommendation?
A book recommendation. The Tao Te Ching.
Yeah, why not?
It's short.
That definitely helps. If you thought this question was hard, I'm going to make it easier and easier as we wind down to the last 3 questions. Yeah. If you could get the answer to one mystery in the universe, right here, right now, today, what mystery would you like to get the answer to? What's that one question that you want to get the answer to?
How did the universe begin? I'm saying that one because it might have an answer I could understand. It's not, I would like to know the meaning of life, but I'm not sure that if it's a question with an answer will you also guarantee me that I'll be equipped with the ability to understand it? Okay. I don't know.
We won't know until we find out.
We don't know until we find out, yeah.
Okay. We'll go with the origins of the universe. What would you like your legacy to be? How do you want to be remembered?
As somebody who loved scientific exploration.
I think that's understating it. You're definitely going to be remembered as that, but also for your incredible contributions to physics. I think your legacy is quite rich already, and there's much more to come, I'm sure. You brought up the meaning of life, so I have to go there now as the final question. You've said in a previous interview that one thread through my life that has served me very well as a physicist, I'm not really a believer, I'm a seeker. So as a lifelong seeker, I have to ask whether you've sought the ultimate mystery, the ultimate question. What is the meaning of life, Andrew Strominger?
Well, first of all, there's quite an assertion there that is the ultimate mystery. I don't know if if that's so, but certainly as a child, I wondered very much about what the meaning of life was, and I think somewhere around 10 or 12, I came to the conclusion I would never know. It was too hard. And I wanted some questions that gave you the feeling you were getting closer to something and that you could be sure about. And that's how I landed in physics.
You now have a hunch what the meaning of life is? Are you closer?
I didn't say that.
Are you closer than where you were at the age of 10 or 12?
I don't think so.
Okay.
Are you?
Well, this project is my exploration into the meaning of life, because every guest I've interviewed, I've asked them this final question. And every episode I get maybe 1% closer. Not 1% is too much. 0.1%, 0.001% closer to the answer just by hearing people's perspectives. And maybe by the 1,000th episode, I'll have the meaning of life ready for you and I'll email it to you.
Okay. I'll be waiting with bated breath.
I'll send that email to you. Professor, if people want to connect with you or find out more about you or your work, what is the best way to find out more?
I listen to your podcast.
Well, that's the best way to find out more. We did cover a lot of your work, and there's even more.
Yeah.
You have an imprint all over theoretical physics. Professor, thank you so much. This has truly been an honor for me.
Thank you. A lot of fun.